Welcome to the lecture for research methods. Today we'll be talking about how to conduct descriptive research. Starting off talking about the goals of descriptive research, talk about two types of descriptive research, simple descriptive research and correlational research. Now, simple descriptive research is where you're, as the name implies, simply describing some phenomenon, right? So not looking at any particular relationships, just generating some numbers to describe something you're studying. So the goals of simple descriptive research, systematic measurement of behavior. Right? So this is different than just going and watching some people interact and then saying, oh, they did these things. That's describing their behavior, but that's not descriptive research. Descriptive research involves systematically measuring behavior, having a plan for what behaviors you're going to measure, how you're going to measure them, how you're going to quantify these things, and that's one thing that makes it distinct from just narrative, right? Just describing behavior of people. An additional goal is to summarize data. If there's you're observing some behavior, some phenomenon, and there's a lot of behavior out there that you're trying to look at, it can be hard to convey what you found, right? To describe the phenomenon briefly. And so often the goal of simple descriptive research is to, in some ways, summarize and boil down some large, complex phenomenon to a smaller set of numbers that can be representative of what's going on. The average amount of whatever's happening, standard deviation, things we'll talk about in a minute. So, systematic measurement of behavior, and then also just summarizing large bits of data. Correlation research similarly involves the systematic measurement of behavior, but then it goes kind of a step further from descriptive research, and it's where you're interested in identifying and quantifying the relationships between or among variables. So, are these variables related? How related are these variables? When you're asking those types of questions, you're looking at correlational research. Okay, let's look just a little more deeply in terms of the goals, in terms of the uses of descriptive research. What's it used for? When's it used? Well, one primary use would be when you want to identify the limits of a phenomenon, right? So before you start hypothesizing about, okay, are these things related, or does this cause this? You just want to know, well, how much of this is going on? So if you wanted to know how many people are using social media regularly, okay, that's just simple descriptive research. You're just gathering some data, finding how frequently something is happening, or what percentage of people is doing something, right? If you want to know, hey, how many times has someone searched "Am I crazy?" using Google in the last month? Simple descriptive research. Beyond that, program evaluation often involves a good bit of simple descriptive research. For example, if we wanted to evaluate the counseling programs at the university, we might go collect some data, finding out how many of the students who graduated last year passed the licensing exam. So it's not looking at which students passed or why they passed, trying to predict things. Just, hey, how many passed, which should be an indicator of how well the program is preparing students for that particular step in their career. Similarly, it can also be used doing needs assessment, right? So if you have some program, some organization that's looking to improve, and they want to know, well, what do our consumers need, right? So here at the university, we might do collect some data, looking at asking students, would you prefer more daytime classes or more nighttime classes? And again, not looking at which students are trying to predict patterns, just saying, hey, do you want this? So how many people want more daytime classes? What percentage want more nighttime classes? That's simple descriptive research. Beyond that, it's often used as a precursor to experimental research. And for simple descriptive research, it's really in the vein of establishing the importance of some research question or some research agenda. Right? So if you want to do some research on helping soldiers who've returned from deployment, you might first have to gather some data, do some research on, well, how many soldiers get divorced within the first year of returning from deployment. Right? That's a simple descriptive research question, and you gather those data, and you could publish that, and then later you would cite that probably when talking about your intervention for reducing divorce in returning soldiers. Right? Or how many school-aged children were diagnosed with bipolar disorder last year. Right? So before doing research on, well, are kids getting overdiagnosed who have these characteristics? Are they getting misdiagnosed because of this, that, or the other? First, we need to establish some baseline of, well, how many kids are being diagnosed with this particular disorder? Right? And again, that goes back to that simple descriptive research. Okay, when you kind of want to go to the next level, in many ways, we're talking about correlation research, which is another subtype of descriptive research. You can also use that when doing program evaluation. But your questions just change a little bit. Right? So you may be asking, is GPA in the program related to the likelihood of passing the licensing exam? Right? So instead of just how many passed, it's okay, can we predict who would pass? Right? In terms of some other indicator of how well someone did in the program. Because the program is doing a good job, then people who do better in the program should be doing better and passing the licensing exam. Right? Or asking, are graduates of the program more likely to be employed after graduation than graduates of other programs? Right? Again, even that kind of group difference is a correlational study. We're just looking, is there a relationship between type of program and employment? Also, needs assessment, you can use correlation research. So instead of that, what time would you like your classes, we could follow up and look at do people who major in psych have the same or different preference than students in business majors, right? So here we're looking at, is there a relationship between your major and your preference for classes, which is a correlational type question. Broadly, if you're interested in predicting some outcome, some behavior, correlation research is often used for that, because the best predictor of future behavior is past behavior, right? So if we can identify these relationships between behaviors at some set point in time, then we assume that that would be true in the future, right? So can we predict who will get complaints against their license based on their grade in ethics class, right? So we collect data on how you did in ethics class, just your grade, right? Then we'd follow up probably with surveys or something, looking, okay, did any graduates get complaints against their license, and say, okay, those who got complaints and those who didn't, did they differ in their grades in the ethics class back in the day? And if so, okay, well, now we established a relationship. Now we think, okay, we've got a new student, they just finished that ethics class, maybe they got a poor grade. Now we think, okay, well, based on our previous data, we're now going to predict that student is more likely than some other student to get a complaint against their license. Now maybe we know they need remediation. Also, quite frequently used as a precursor to experimental research, but maybe for some different reasons than simple descriptive research. Correlation research often used when you're interested in kind of cause and effect, but it's unethical or impractical to manipulate an independent variable. Right? So if you want to look at, you're interested in the effect of losing a parent early in life and attitudes toward parenting, you can't randomly assign people to lose a parent or not lose a parent. Right? You can't take away people's parents. It's unethical and impractical. Right? So you're unable to conduct an experimental study looking directly at that question, but you could measure those variables and do a correlational study. Which if you found a relationship, you may then work a little harder to try to come up with some sort of analog experimental research. Also, sometimes you use it when you want to identify the most likely causal agent, right? So you have something, well, I think I want to know what causes success in therapy. Is it what part of the therapy experience? Is it how experienced the therapist is? Is it therapist self-disclosure? Is it therapist availability outside of session? And if you're going to do an experiment trying to manipulate all these things, it can be quite complicated. So instead, you might do a correlational study where you can measure all of these things at once and see which one emerges as the strongest predictor of success, and then go do an experiment saying, okay, well now if we manipulate this thing, this one that was the best predictor, is there a causal relationship there? So the most likely candidate for being a causal agent, correlational research is good for that. And last, when you're interested in multiple levels of a variable, right? Think about a dose-response curve, where, because in an experiment, sometimes you think, okay, I've got this group versus this group, so placebo versus drug, or low versus high. Well, what if you want to know, well, what about 3 sessions of therapy versus 6 versus 9 versus 12? And again, the more you do this versus that versus this, each one of those you have to have, each level of your independent variable is a separate group of people, and for each group you have to have a certain number of participants, and so you end up having to have a pretty large study to be able to look at differences at different levels of a variable. Whereas in correlational research, especially if you're looking at some sort of continuous variable like number of sessions, you can look at the relationship between those number of sessions and number of symptoms on a kind of continuous basis. So at all levels of number of sessions, okay, when do the symptoms start to drop? And you don't have to look at this many versus this many versus this many. You're looking at all of them at once, and you can do so with much fewer participants. Okay, where do the data come from for correlational studies? Lots of places, depends how you want to do it. There's ex post facto data, which is typically whenever you've already conducted a study for some other purpose, and you've got some data you weren't initially interested in exploring. So maybe you had an independent variable, dependent variable, and you had some demographics, and the demographics you just collected because you knew you're supposed to collect them. And now you finished that study, you published it, and you look back and you go, gee, I wonder if there was a relationship between gender and our dependent variable. Now you're going back ex post facto, after the fact, and looking at relationships on this existing data. The quality of the research depends in large part on the quality of the data from the original study and how well it suits your current purpose, right? Because when you were collecting the data initially, you weren't planning to look at a particular relationship, you may not have collected it in a way that really best represents the construct validity of the construct you're now interested in. So, in terms of, is that good or is it bad? It depends. It depends on how you collected the data and if it fits with your kind of new research question. Archival data, and that's really any data that were collected for some other purpose, usually not for research, right? So if we're interested in the relationship between students' SAT scores and college GPAs and some other things, you didn't take the SATs as part of a research project. You didn't earn a GPA as an undergraduate for research. But those data are out there, and we can access them if we get your permission, or medical records, anything like that. It's data that's out there somewhere in some format. It's in an archive, and you can go in there and look at relationships between variables. Now, the data that are in archives often differ in terms of whether or not they're already coded or uncoded, and that basically means in numerical usable format for quantitative analyses, or uncoded, not in numerical usable format. Right? So when data aren't in a format that lends itself readily to analysis, like maybe you're looking at essays written by students applying to graduate school. Right? You're looking, okay, did students wrote this type of essay versus this type of essay, eventually were they more successful? Right? Typically what you have to do is you have to go back and develop some sort of coding system to transform the data into numeric format. Right? There are multiple approaches to do this. One of the most common is something called content analysis. It's this kind of ground-up approach where you read the essays, identify themes, then train others about what these themes are, and then you have them code the essays for the presence or absence of these themes. One of the just kind of good things about archival data, they often provide information that would be difficult to gather otherwise, right? Statistics on driving fatalities, it would be hard to wait out on the highway for people to die. Kind of gruesome too. You know, things like that, any kind of data that involve long time periods, much easier to use archival data than to wait for several years for those data to observe them firsthand. On the flip side, the data weren't being recorded for research, so they probably weren't recording them as experimenters would. So maybe not quite as carefully, not so much worried about bias and interpretation of something, whether it fits into this category or in that category. They weren't collected scientifically, so that is a bit of a drawback for archival data. Another source would be observation, right? And different types, excuse me, of observation: laboratory, naturalistic, participant observer. So laboratory, that's just in some controlled setting, not necessarily in a room that's called, oh, this is the lab with your black countertops and white walls. It doesn't have to be that, but any kind of controlled environment could be a laboratory where you're doing observation. And we have some really good data from observational studies in kind of laboratory settings. A lot of the data, early data on attachment with Ainsworth and the strange situation where they have the parent come in with the kid and then to a strange room, and then the parent would leave the kid and leaving them in a strange situation, and then the parent would return, and you'd observe what the kid would do, and based on that they would classify the kid as having some different type of attachment style, right? So hugely formative research based on this laboratory observation. But again, the lab was more like a playroom. It wasn't a science lab as you may traditionally think of one. The benefit of that obviously is you can control more things, but the more things you control, the less external validity, ecological validity you have. So you could try to do naturalistic observation, which is great for external validity, but if it's naturalistic, it's really hard to control things, and so you can get a lot of other noise in the data. And then participant observation, it has its pluses and minuses. Sometimes there's certain groups that are just hard to observe unless you join them. Like if you wanted to know, hey, what's going on with these some religious extremists, they're typically not very open to being studied or filling out surveys, right? They're not really going to let you watch them. But if you pretended to be one of them, you could maybe gather some data. With some ethical concerns about that, and then also you can't be sure once you join the group if the group was or acts and displays the same behaviors as they would if you weren't there. Because if you're participating, you are affecting, you're impacting their behavior. So that's one of the problems with that particular type. And in general, using observation as a source of data, the things you worry about are reactivity, right? Which is that just in general, when people are being observed, whether if it's participant observer or naturalistic observation or lab-based observation, when people are being observed, they tend to act differently if they know they're being observed. Right? And there's a lot of data say, well, after a while people get used to it, but there's still sometimes some artificiality to their behavior when they're reacting to that being observed. Right? The other thing is the potential for biased interpretation. Right? Similar to we talked about when dealing with archival data. When you observe something, you say, okay, oh, that when they put their hand on their shoulder, that meant this. Okay, there's some level of interpretation there, right? And you're deciding, okay, yes, aggression was present, no, it wasn't present. Yes, affection was present, no, it wasn't present. So it's a little squishier than having other sources of data maybe. So what else can you use? Tests, which are existing sets of questions that have previously been administered to enough people that there are data existing regarding what answers to the test questions mean. And when I say enough people, I'm talking about they've been standardized. They've been administered to a normative sample. And so before you could use the Beck depression inventory, they went and gave it to a bunch of people to figure out, okay, along with a bunch of other measures, to say, okay, high scores are correlated with this, low scores are correlated with this. So if you're between here and here, this is kind of what you look like. If you're higher, this is what you look like. So you know what scores mean because they've been given to a large group of other people. Right? So that's what tests are. So existing published or unpublished tests, they've been used before, which differs from surveys. Surveys may look the same, but they're sets of questions typically that you create or someone else has created that hasn't yet been standardized or normed. And the quality of the data depends on the quality of the questions. And we could spend a whole year working on how to construct an appropriate survey that wasn't biased, didn't have leading questions or double-barreled questions, wasn't too long but also wasn't too short, right? Adequately assess the construct without boring the participant. It's a real combination of science and art to designing an effective, valid survey. That's why we often rely on professionals to develop these tests instead and use them to try to make our own. Okay, quick concept check. What do simple descriptive research and correlational research have in common? Two things. They both involve systematic measurement of behavior. And the other thing is they're both descriptive research, which means they're both non-experimental. You're not manipulating a variable with either one of those approaches. Second question: what is reactivity? Okay, we just talked about that. That's the phenomenon where individuals change their behavior because they are being observed. Okay, how do you analyze the data from simple descriptive research? Often, in terms of summarizing data, looking at things like measures of central tendency, so mean, median, and mode, where mean is just your arithmetic average, so you add up all the numbers and divide by the number of observations you had. The median being the middle number, so if you take all the numbers, you put them in order from least to greatest, and then count toward the middle from either side, and that middle number is your median, which sometimes you prefer the median to the mean. If you have some extreme outliers, they're going to pull that mean, pull that average one way or the other. When that happens, the median may be a better representative of central tendency because the median isn't affected by huge outliers. And then the mode is the most often occurring value, right, which sometimes can also be an informative number. Usually it's most interesting whenever it's different from, significantly different from the mean or the median, right, where something's happening where almost half the group is putting one particular value, but there's enough values far away from it that's pulling the mean away from that, and maybe the median somewhere else too. So all three are used, but the one most commonly used and most representative, typically, of central tendency is the mean. Especially if you have a normal distribution, they'll all be the same number, which is nice. In terms of measures of variability, there's several. The two most commonly reported, standard deviation and range. So standard deviation, there's a formula for it, obviously, but basically it's the average amount that a score differs from other scores in a data set. Right? So it tells you how spread apart they are. The bigger the standard deviation, the greater the variability. The smaller the standard deviation, the smaller the variability. And range, obviously, not all about obviously, but Range is the maximum minus the minimum, so how far apart the greatest value and the smallest value are. And you have other types of range, like interquartile range, and you can look at, okay, at 25%, what's that number? At 50%, at 75%, what values are there? But typically you just see the standard range. Other descriptive measures you might see or use when doing simple descriptive research. Percentages, so the percentage of people that reported this, so kind of frequency data. Related to that, percentile rank, right? So, you know, if 100 people took a test and they say, oh, you're in the 90th percentile of scores, that means obviously you scored better than 90% of people, and 10% of people scored better than you. And then standard scores, which especially if you are using any kind of you know, norm tests to gather your data, you may get a standard score. And that just means that the raw score, so how many questions you got right, is then transposed into this standard score that tells you where you fit relative to the normative sample, right? Often in clinical settings we see things that they're normed where the average, so if you got exactly the average score on some measure of anxiety, you'd get a standard score of 50, right? And then the standard deviation of the standard scores is 10. So 2 standard deviations above the mean is 70, 2 standard deviations below the mean is 30. Right? So sometimes you see these cutoffs where, okay, you know, on the scale, if you get a 70 or above, so 2 standard deviations above, that's clinically significant, and that all that means is, okay, you're in the top, you know, 2.5%. Okay. When you want to analyze data from correlation research, a couple of things you can look at. One, if you're interested in bivariate correlation, so the excuse me, the correlation, the relationship between 2 variables. Most often you'll use the Pearson R, not always, but most often, and you'll use the Pearson R, which there's a little graphic of it, when you have 2 continuous variables that you want to know, are they related. So if both variables are measured on an interval or a ratio scale, you use a Pearson R. If they're measured on some other scale of measure, ordinal or maybe nominal, you're going to have to use something else. But if they're both continuous, you can use the Pearson R, and it looks at the linear relationship between 2 variables. So as values on one variable increase, what happens to values on the other variable? Do they also increase or do they decrease? And you generate the Pearson R coefficient from that, and the R can range from a -1 to a +1, right? With 0 being in the middle. If 2 variables are not related at all, you'll see an R of 0. If they're positively related, and the picture we have here, it shows an R that was probably close to 0.8, maybe 0.9. Pretty good correlation, and it's positive, right? Where you see as you increase on the x-axis, which is going to the right. So as you go to the right, from left to right, the line the best fitting line for those data points goes up, right, on the y-axis. So up on one is up on the other. That's a positive correlation. Negative correlation means when you go up on one, you go down on the other. So to the right and down, or to the left and up, but in opposite directions. What else about bivariate correlations? There are other coefficients you may use. Again, depending on how your variables are measured, if they're ordinal or if they're nominal. Maybe you're looking at gender. If you're looking at, well, biological sex, male, female, and you're looking at kind of this dichotomous variable. So you might be looking at a Spearman's rho, Kendall's tau, a point by serial, eta. And eta, those first ones are for different types of data. The eta is for a different type of relationship. You're looking at Instead of a linear relationship, a curvilinear relationship, that's a different correlation coefficient. So there's lots of different correlation coefficients, and I'd say 90% of the time you're going to use a Pearson R. But if you have data that are a little different, that aren't continuous, or if you're looking at maybe a non-linear relationship, you got to do some research and figure out what the appropriate correlation coefficient is. Whatever correlation coefficient you use, for many of them, you can typically generate a coefficient of determination, which is just the square of the correlation coefficient. So for Pearson R, it's R squared. And that coefficient of determination is a couple things. One, it's an effect size. We talked a lot about those. The other thing it does is it tells you about the percentage of variability in one variable that can be explained by another variable. Right, so if two variables have a correlation of 0.9, then the R squared is 0.9 times 0.9, which is 0.81. So 81% of the variability in one variable can be explained by variability in the other variable. And R of negative 1 times 1, negative 1 times negative 1 is 1. So 100% of the variability in one variable can be explained by variability in the other variable. R of 0 times 0 is 0. So none of the variability in one variable can be explained by variability in the other variable. So that's what the coefficient of determination gives you. Okay, if instead of looking at relation between just two variables, maybe you want to look at multiple predictor variables and one criterion variable. If so, you're looking at probably conducting a multiple regression analysis. Excuse me. And there's different types of regression analyses. Two of the most common are stepwise and hierarchical. In stepwise, basically you have a bunch of predictors, and you're going to throw them all in at once, and they're going to fight it out to see which one is going to emerge as being most strongly related to the criterion, and it gets to go in first and eat up as much variability as it can. And then the rest fight out and say, okay, of what's left, I'm the best predictor, and then the next one, and that way you end up getting, okay, this predicted the most, and then this, then this, then this, and together all these variables predicted the criterion this amount, right? So you get an R squared for regression. I can account for this percentage of variability in the criterion using all of these predictors at once. Then you can also look at these beta weights, which are like they're partial correlations. They're basically sort of like the correlation between each predictor and the criterion by themselves, but it's by themselves when accounting for the other predictors, which it makes regression unique from just doing a bunch of correlations. In stepwise, it's different from hierarchical. Stepwise, they fight it out. In hierarchical, you put in variables in particular order. So oftentimes you do that when you say, okay, I want to show how much this variable predicts the criterion after these other variables have already been entered. So after accounting for the relationship of SES on this variable, this other variable now predicts even more variability in the criterion. So when you have some sort of theoretical, logical reason to put variables in a particular order, you're talking about a hierarchical regression. Okay. A lot of times people think, okay, correlational research, so correlation coefficients, maybe regression, sure, that's all you do. Not so much. You also may be looking at the mean difference between groups, right? And so you're talking about things like t-tests or ANOVA, right? With t-tests, you have your independent groups t-tests, your dependent groups t-tests. And ANOVA is whenever you have more than two groups you want to compare, so 3 or more. And oftentimes you think, oh, ANOVA, that meant if I do an ANOVA, that means that I did an experiment. No, that means you're looking at group differences. If you're looking at group differences, but you didn't manipulate an independent variable, that's a correlational study, right? You're looking at the relationship between two variables that where you didn't manipulate anything. That's non-experimental, that is correlational. Okay, so those are frequently used in correlational studies. Also, if you're looking at, if your data are frequency data, the number of times something happened, number of observations, you're talking probably about chi-square. There's also the Mann-Whitney U, but most commonly chi-square. Two types of chi-square I want to touch on. the chi-square goodness of fit test, right? And this is whenever you have the frequency data for one variable. It has at least 2 levels, which makes it a variable, and you want to compare your observed frequencies to some theoretical or known frequency, right? So maybe you have some normative data on what percentage of people in a group should be expected to have a secure attachment. Okay, so this instrument on attachment's been used several times, and we now know that 59% of people have secure attachment. Okay, so that's a known kind of theoretical percentage. So then you could go collect data on a group of soldiers returning from deployment, measure their attachment style, and compare what percentage of them has secure attachment to this known percentage. And to do that, you would use a chi-square goodness of fit test. So you have a known percentage compared to the thing. If you wanted another use of it would be, say, I wonder if people prefer online classes to face-to-face classes. Right? And you could ask people, how much do you prefer this, how much do you prefer that, and then you'd have this nice continuous data. You do a t-test. But if you just had people raise your hand, and so now you have number of people that prefer one thing versus number of people that prefer another. Now you're talking about frequency data. You can't do a t-test comparing frequencies. T-tests are comparing means, right? So for that, you could also use a chi-square goodness of fit test, where the null hypothesis would be, okay, well, if there was no preference, then you'd get 50% in this group and 50% in that group. So you compare your observed frequencies to that theoretical distribution. Okay, so that would be a second use of the chi-square goodness of fit test, as compared to the chi-square test of independence, which is even more akin to correlational, your other kind of correlational research. Almost think about, almost like ANOVA, a little bit like Pearson. This is whenever you have the frequency of 2 different variables, right? And each of those variables has at least 2 different levels. So maybe you want to know, is a person's preference for type of soda? So which one of these 4 is your favorite sodas? So I've got a number of people like Coke, a number of people like Dr. Pepper, a number of people like Sprite, yada yada, right? And then I ask those same people what their favorite TV show is, and I give maybe 4 choices again there. Okay? And I want to know, okay, is your choice in soda related to your favorite TV show? You think, well, that's a dumb question. It might be a dumb question, but you could be looking at the effectiveness of product placement, right? Where if one particular show, well, this show always features Sprite, and this show always features Diet Coke. If product placement is being effective, then we should see a relationship where, okay, people that like this show also like this soda, right? And to answer that question, you would do a chi-square test of independence to see, okay, are these 2 variables independent or are they related? And you're hoping they're related, typically. Okay, another real quick concept check. If 2 variables are perfectly correlated, so think about two continuous variables, calculating a Pearson R, what would you expect the R value to be equal to? Okay, and many of you probably said 1, and hopefully most of you said, well, positive 1 or negative 1. Both of those typify a perfect correlation. Right? Just one's a perfect positive correlation, one's a perfect negative correlation. Right, both perfect. Now, if the Pearson R describing the correlation between 2 variables was R equals 0.70, how much variability could you explain in one variable using what you knew about the other variable? %. How did we get that? Coefficient of determination, right? So R squared, 0.7 times 0.7 is 0.49. 0.49 is 49%. Alright, last one of these. If you watch people walking into a department store, right, and you want to know if there was a relationship between gender, men versus women, and fruit preference, strawberries versus bananas. Very important question. Not right. What analysis would you use? Right? So you have 2 variables, and you have frequency data. So you're looking at a chi-square test of independence, right? Okay, so now we know how to analyze. We know which tests to use for different types of correlational approaches. How do we interpret what we found? Can we infer causation from correlation? No. And why not? Two main problems: directionality and the third variable, right? Just because directionality says just because A and B are correlated, we don't know that A causes B. A could cause B, or maybe B causes A. We don't know which way necessarily the direction arrow points if we didn't assign people to groups and manipulate an independent variable. Second problem is the third variable problem, right? So again, A and B are correlated. Well, did A cause B? Did B cause A? Or is there some third variable that explains that correlation? Well, really, A causes B and A causes C and C causes B, and because of that, A and B are related. But there's no causal relationship there at all. Right? So we have to be cautious about inferring causation from correlation. And that's not to say that all these things are correlated. There can't be cause and effect. There might be cause and effect. We just want to overinterpret that. Oh, there is. It's a maybe. Because typically, if there is a causal relationship, we should be able to identify a correlational relationship at some level. Another thing to keep in mind is you need to know about the relationship between doing multiple analyses and finding false positives. The more, and this is true for correlation research and other types of research, the more tests you do, the more likely it is that eventually you're going to make a type 1 error. And that's just a statistical thing where there's this family-wise error rate where the likelihood of making error increases the probability increases at a fixed rate, at an exponential rate, but a fixed exponential rate. So you don't want to say, okay, I'm going to measure all this stuff and I'm going to calculate bivariate correlations for all the variables in my study, and I'll see which ones come out significant. You're really kind of cheating there, and that's bad science. So you want to only examine the ones that you think should be correlated. Right? Don't use that scattershot approach where you calculate every possible correlation. If you do calculate every possible correlation, and many people do, what you need to do as a responsible scientist is to account for the fact that now you've inflated the type 1 error rate. And you do that by changing your alpha. So okay, so your alpha is 0.05. I'm going to do a couple of tests. So instead of using 0.05, for each test I'm going to use 0.01 or 0.001. And sometimes people will just bump it down like that, kind of somewhat arbitrarily. But there are also some people make the argument for using a particular adjustment to alpha, where sometimes you'll divide by the number of tests you're doing or other variations of that, which some people would suggest better account for that family-wise error rate. But there's lots of disagreement about that in the field. General acknowledgement, you do have to worry about it, but how to fix it in terms of adjusting your alpha, lots of different opinions. Another thing to keep in mind is the possibility of insignificant significance. And here I'm talking about where you have a statistically significant correlation or a statistically significant difference between two groups in some correlational study that is really not significant, not meaningful, right? And that happens usually if you have a very large sample. You could get a correlation where, okay, the R is equal to 0.2 and it's statistically significant at the 0.04 level. So, okay, yeah, so the p-value is fine, it's statistically significant, but when R is 0.2, the coefficient of determination is 0.04. So you're accounting for 4% of the variability in your criterion with your predictor. 4%. That's not a lot. That may not be very significant. And I say may not because it depends on what you're studying, what the variables are. Sometimes accounting for even a small amount of variability, if it's unique variability, well, we can add the prediction of some outcome by throwing in this variable a little bit. Sometimes that's huge. It depends on what stakes you're playing for in terms of what the criteria is. But often it's not, so you want to keep that in mind when reporting results of correlational studies and other studies as well. The other thing to worry about is when you don't get statistical significance. So your non-significant findings, your null findings. And this can happen sometimes because there's not a relationship, right? And if so, okay, good, you did good research. You correctly showed 2 things weren't related or 3 things weren't related. Great, super happy. But sometimes it's not because they weren't related, it's because you failed to find it. And that can happen for a couple reasons. One, if you have insufficient power, which lots of things contribute to power, which we'll talk about over time. One of the biggest ones being sample size. If you don't have enough people in your sample, and usually it's not enough people for the number of groups you're working with, or for the number of variables you're working with, you may not detect a significant relationship. Also, if you're using bad measures, that can screw up your power as well. The other thing, restricted range, right? So having a truncated range. If there's no variability in your sample, so if you're looking, okay, does the amount of caffeine consumed predict GPA? So if everybody drank exactly the same amount of caffeine, right? You didn't assign them to, you just asked how much caffeine you drink. If everybody drank exactly 1 cup, they're not all going to get exactly the same GPA. Doesn't mean there's no relationship. It just means that you couldn't find any relationship, right? If caffeine were the only predictor, then yeah, you should see them all get the same grade. But it's not the only predictor. But you won't see that relationship at all because you have no variability in caffeine. You'll get a correlation of 0. It's just a mathematical thing where you can't predict variability without having some variability. So you have to have variability in both your predictor and your criterion. If you have a truncated range, not enough variability, you're not going to find a relationship. And then also, there's a possibility of fluorine ceiling effects, which we talked about last time. You also have to worry about potentially insensitive measures, right? So maybe there is a relationship, but you didn't detect it because you measure things too grossly, too macro a level, and the relationship is going to be seen only when we get to those kind of fine-tuned distinctions. And then the last one is the possibility of a non-linear relationship, right? And this is basically if you're using the wrong correlation coefficient. So if you're using a Pearson's R or even a Spearman's Rho, those look at kind of linear monotonic relationships, kind of going in one direction. Whereas non-linear relationships, like the relationship between anxiety and performance, where okay, at first you've got this, well, okay, as anxiety goes from low to high, performance is better, right? Because if you don't care at all, I'm not going to study, I'm not going to do well. The more I get worried about it, the harder I'm going to try, the better I'm going to do. Up to a point. Then you start to freak out, and performance starts to come back down. Right? So you could have that U, you could have that's an inverted U, you could have a regular U, it could be kind of this exponentially increasing or decreasing function, but anything that's not linear, it may not show up as and especially if it's a U, it won't show up when you're looking at it with a correlation coefficient that's designed to detect a linear relationship, because the best line that fits for this U is a flat line, right? And a flat line is a 0 correlation, right? There's no slope. So sometimes, in the way you figure that out is you look at a scatter plot of your data, right? So, and you can do it by hand, or you can use whatever statistical software package you're using. Typically, they have that thing where you can plot your data using your predictive variable and your criterion variable and see where the dots lay. It's okay, does this generally look like there's some sort of linear function, or does it look like there's something curvilinear? And if it looks curvilinear, well, you got to pick a different correlation coefficient. Okay. Now, we've said over and over, and I'll keep saying it, you cannot infer causation from correlation. You cannot infer causation from correlation. But you can do things to try to improve the internal validity of a correlation study. you can't do everything perfectly and say, okay, well, I did these things to improve internal validity, and now this correlational study is as good as an experiment, and I can make cause-effect statements. You can't do that. You're always going to be limited by the fact you didn't do the things you needed to do an experiment and have that amount of internal validity. But correlational studies can differ in how much internal validity they have. A couple of things they differ in terms of whether or not there's some sort of temporal association that can be made. So if you can use any sort of longitudinal design where you're able to measure your predictor before your criterion, right? So you can show. So if you show, for example, that okay, I didn't do anything to these two groups, but I measured them at time 1, and they were exactly the same on some variable, or on these two variables, predictor and criterion, and then a year later, the predictor variable happened differently to one group than the other, and after that, the two groups differed on this criterion variable. Okay, that's a little stronger evidence for causation than if you didn't have, okay, well, we knew they were equal at the beginning. So if you have that temporal association, that helps, which sometimes you can find that with doing archival research. The other thing to do is to measure that excuse me, potential third variable or third variables, right? So, well, because all you do is you think, okay, I think I'm going to see if A and B are correlated. And people say, well, it may be that, but it may be that A causes B, which causes C. So you anticipate what that third variable might be, and you measure it. Okay? And when you do that, a couple things you can do. You can just measure it in your study, nothing else, and then kind of post hoc after the fact, you examine it and say, okay, well, was A related to C, which was then related to B? And if not, you can say, well, that alternative explanation didn't hold water with this group. Not true. So therefore, you got rid of at least that one naysayer. That strengthens your evidence. Okay, maybe A and B really are causally associated, at least in terms of doing away with that one explanation. Another thing you can do is use a matched groups design. So when selecting your sample, you create groups that are similar on important variables. Right? So if one guy in group A has high IQ, you find someone else that has a high IQ to be in group B. Right? So you say, okay, well, people can't say, oh, well, these groups may have also differed because they were different on IQ. No, I made these groups equivalent using a matched groups design. At least on some variables. You can't do it on every variable. The more variables you try to do it on, the more expensive and time-consuming it will be. But you can do it on some major ones at least. The other thing you can try to do is use some sort of procedure to statistically control for differences on these variables. And this is things like regression, so like using that hierarchical regression where we say, okay, well, I'll go ahead and put in this variable first and say, okay, well, can I predict above and beyond that? If so, then you can't say it's just this other variable. I've already used the variability, that one explains it all up, and I still predict above that. Another thing is use ANCOVA, so using a covariate, which I'm not real fond of that method, just mathematically, statistically. What you're trying to do is okay, well, what if all these people were the same on SES? And so you're basically changing their scores on one of the variables up or down based on what the relationship between SES and that variable, to imagine, okay, well, if everybody were the same. But everybody's not the same on SES, and you can't mathematically create sameness. You can create the appearance of sameness. That's what ANCOVA tries to do. But that's not the best use of ANCOVA, so I wouldn't recommend ever doing that. The other thing you try to do is establish the equivalence of groups, and you actually, the matched group design is doing that some. Beyond that, you might just be measuring a bunch of things, where you've got these two groups, and maybe you don't have that longitudinal data where, okay, they were the same on this variable and now they're different, but they're the same. The two groups were equivalent in age, they were the same in SES, they were equivalent in exposure to some particular type of media, whatever. All the things people say, okay, well, two groups might also differ because of this. You could say, well, we measured all these things and they are actually equal. That's the kind of thing where if you don't do a matched group design, you try to recruit them as equal, and then you hope that they're equal when you go to measure them at the end. And the last thing you can do is really focus on construct validity. It's all about controlling what you can control. You can only do so much for internal validity, but when doing correlation research, you can make choices regarding, if you're not doing archival research anyway, if you're collecting data yourself, original data, you can decide how you're going to measure things. And the degree to which you have good construct validity will limit the level of internal validity you have. Right? So, if nothing else, focus on getting really good construct validity. If ultimately your interest is in establishing some kind of cause and effect relationship, which again typically you would have a follow-up study after your correlational study, where then you do an experiment. Excuse me. Okay. In terms of when you want to look at the relationships among multiple variables, we'll talk about this just briefly. We already touched on one approach, multivariate regression. So in multivariate regression, you're looking at a bunch of predictors in one criterion, right? And how do all those predictors combine in some linear fashion? So, they combine to form this, almost like there's one mega variable that predicts the criterion, accounts for some amount of variability in the criterion variable. And okay, that mega variable is made up of 40% variable A, 20% variable B, 10% variable C, so on and so forth. Right? So multivariate regression, great for when you want to know, okay, which thing is the best predictor of something. If you want to get a little fancier than that, basically a multivariate regression using, imagine it with a mirror, where instead of a bunch of predictors in one criterion, you have a bunch of predictors and a bunch of criterion as well, so multiple variables on both sides of the equation. That's what a canonical correlation does. And so that looks at, okay, how do these variables on the left side form into these mega variables to predict these variables that are going to form on the other side. They're going to join up to form kind of, okay, all these variables, we had like several measures of anxiety, several measures of depression on one side, and then several measures of cardiac health, and several measures of maybe skin health on the other side. And we probably hope that the anxiety measures will kind of bond together to form a variable, same with depression, and then the cardiac measures go together and the skin measures go together. And then look, okay, how do those variables, then after they've kind of coalesced into these canonical variables, how do they then relate to the things on the other side of the equation? And that's when you're really looking for kind of complicated relationships. There's multivariate analysis of variance, or MANOVA, which is, ANOVA, which is really univariate analysis of variance, is when you have you can have more than one independent variable. It's still ANOVA. Well, sorry, univariate ANOVA is one IV. Factorial ANOVA is multiple IVs, but those are very similar. But they're both very different from multivariate ANOVA, because both univariate ANOVA and factorial ANOVA, you only have one dependent variable, right? So do these groups differ on this one variable? Multivariate analysis variance says, okay, do these groups differ on some linear combination of these dependent variables? Right? So kind of like, mathematically, very similar to multivariate regression. Okay. And then using some combination of these approaches, excuse me, you can look at things like moderation. Right? You can use regression or ANOVA for this. And this looks at, okay, I think there's a relation between A and B, but I think that relationship, what it looks like, depends on the level you're at on some variable C. Right? So maybe A and B are related when C is low, but A and B are not related when C is high. Or A and B are positively correlated when C is low, A and B are negatively correlated when C is high. Right? So the nature of the relationship between two variables changes at different levels of some other variable. If when that happens, that other variable is moderating the relationship between two variables. Right? You can look at that with regression. You can look at that with ANOVA. Another phenomenon you can look at with these procedures is mediation, and that's similar to moderation but different. So instead of some variable moderating, so okay, at different levels of this variable, this other relationship changes. Mediation is where, okay, A and B are related, but that's because A causes C, which causes B. So it's that kind of classic third variable problem I always worry about. That's usually mediation oriented. So, okay, yeah, this caused this, but it only caused it because it caused this thing, which then caused that thing. Okay, so summing up, kind of the highlights, correlational and simple descriptive research. So descriptive research in general, often used as a precursor to experimental research, because ultimately one of our most important or most burning questions are about cause and effect. We want to know, why did this happen? Can we make this happen? But there are several hurdles to get to jump to do good experimental research. It can be expensive, time consuming, and so often if we're going to do that, we really want to have some good evidence and have a good idea. Okay, I'm pretty sure this causes this. We want to have some statistical, some mathematical evidence of that before we go to all the trouble of conducting an experiment. And that's where often descriptive research comes in to kind of give us that support and that justification for doing an experiment. Correlation does not equal causation. Correlation might indicate causation, but you cannot infer causation from correlation. Right? Can't say that enough. And the other thing that hopefully stood out to you was correlational research, in particular from simple descriptive, is more than just correlation coefficients. Right? So the type of test you're using does not dictate what type of research design you have. Right? So ANOVA can be used in correlation research, it can be used in experimental research, it can be used in quasi-experimental research. The type of analysis used depends on if you're looking at group differences or relationship between variables, and on the nature of the variables you're studying, depending on the scale of measure and if it's categorical or continuous, those types of things. It doesn't what analysis you use is not directly related to your research design. So correlational designs make use of a wide variety of data analytic techniques. Okay, that's all for now. Take care.